So let me start by reminding you that this coming Saturday, we have a test. So if you go to course outline, which was lecture 1, you will see that on 21st, on this Saturday, we have test 3. I also send you an announcement that because of this physics midterm, this slight overlap with the physics midterm, I sent you an announcement that the test, instead of original advertised at noon, it's going to be at 30 minutes later. So 12:30 this coming Saturday, and it's going to be 15 minutes longer. You're going to have 15 minutes extra. So it's going to be 1 hour, 45 minutes. And then you have 15 minutes to submit, and then the server closes. So that's one announcement I'm going to get to, Maid. Another announcement is hopefully what you have seen is that also I posted addition to lecture 16, because what we didn't manage to cover is sorting, in particular selection sort, and a bit of more memory relating to swapping. So you get used more to these memory problems. So that lecture is about, so there's additional lecture of 15 minutes. You're required to know it in a sense, it's a mandatory lecture. So it's 50 minutes extra for lecture 16. So the code and the video I prepared and I posted, so please do watch it. So another thing that I wanted to say is that if you type in Google UOrava dates, you're going to get to this webpage with important academic dates and deadlines. And if you click on this semester and you click on enrollment, courses, withdrawal and reimbursements, you will get here and see that this coming Friday, November 20th, is the deadline to withdraw from a course. The reason I'm mentioning this is that you should consider withdrawing as a tool. It's just another tool for you to succeed. If you see that things are not going well, that you have too much work, that whatever the reason is, what I would like you to consider is kind of realistic situation that you currently in the course. By now, you almost have 50% of your grades. So you basically have the grades from half of your test, and you have the grades from half of your assignments. Some of you have even more grades than half of the assignments. Some of you may already have grades from 4 out of 6 assignments. Most of you will get a grade this week for assignment number 4. So that means that you should have a good estimate of what your final grade may be. So typically, you know, if in the first 50% of the course you got a certain grade, it's likely that it's going to be something similar, and the material is only getting harder. So I'm not trying to scare anybody. I'm trying to get you to make a decision based on whatever your personal situation is. And when you withdraw from a course, there is no, doesn't become a part of your average. And the course is offered again in the winter semester. For those who are worried about the course after the ITI 1121, then that one is offered in the summer. So you can catch up, right? Okay, so that's all I want to say about it, such that you're aware of your options. So the withdrawal deadline is Friday, your test number 3 is on Saturday, and your assignment number 4 is due on Monday. I assume that you will ask me, some of you, what material will be covered in test 3. So everything up to today. So today we are going to do sets and dictionaries. You're not going to have sets and dictionaries on tests. So everything up to today will be on the test. So I think that's all that I had to say for administrative things. I see a hand raised by, let's say, Dat.
Hi, Professor. Can you hear me?
Yes, go ahead.
So what is the procedure for dropping a course?
That I don't know the details. That you can ask, it's probably in your Eurozone. You can, you know, there is probably in Eurozone option to drop a course. I'm sorry, I really don't know that, because, and it's kind of, it's kind of unfortunate because professors and students, we are on a completely different system. So you guys use this Eurozone. I have no idea what this Eurozone look like and what you can do. I would imagine that maybe you can ask it on Brightspace, and some other students, you can ask, some other students may answer if they know how to do it. Otherwise, contact the undergraduate studies office or faculty engineering, and they will for sure know. But by now, they shouldn't be that busy anymore.
I think you can go into enroll on Uzone, and there's an option to drop classes.
Right. Yeah. So I think, as I said, really, I keep on always saying this, you guys are infinitely young. It's much better that you find a plan. If you like this, especially, how do you succeed it? So make decision based on kind of facts of your current situation. It's not easy in this COVID time. So make a situation based on whatever you're in. If you're doing great, not. If you think this is not going so great, I should do this again. Just drop a course. It's not going to be part of your average, and you take it again. That would be my suggestion for those who think that based on the current grades they have, it's not going so great. Okay, Jason.
Hi, Ms. Vida. Just a quick question. To prepare for this test, what practice do you think we should do in the book?
So I guess what we covered.
Because last time you said it was like chapter 5, so I'm just wondering if this time.
So I don't know what the chapter is. I should look, but why don't you ask it on Brightspace? So then I'll look at the chapters again and see if there's extra things to do. I would certainly go through all the labs that we have done so far, including this week's lab, because it's still on the list and stuff and not sets and dictionaries. So today we're going to do sets and dictionary. On Wednesday, we're already still going to start with objects. So everything up to now I would work on. But for the book, if you want extra exercises, the best thing, that's a good question. You should ask me in the Brightspace. So then in the free time, then when the class is over tomorrow, I'll go through the book or other sources where I can find some relevant problems for you guys.
And also, the additional video that you posted on lecture 16, that will also be on our
sure.
class, right?
I mean, this is sorting. It's part of a list and stuff. It's just another problem to solve on the list, right? That I didn't manage to cover. Yeah.
Okay, for sure.
Okay. Okay, so let's start with the lecture. So today, as you have heard, we're going to do sets and dictionaries. Sets you have seen already in mathematics courses. So, in fact, you have seen it before university, in high school, possibly even in primary school. So does somebody remember a definition? What's a set?
A set is a collection of objects that has no duplicate in them.
Exactly. So there are actually two conditions, two main conditions for a set. One is that there are no duplicates, so it's a collection of distinct elements. There are no two that are the same. There's another condition on a set.
The order doesn't matter.
Ordered.
Exactly. So it's an unordered collection. So this is in fact the first time that we are working with unordered collections in Python. Let me start idle. And so where are we? This is the lecture. Let me start with this set, section B. All right, so that part we're gonna get to. But first, let's see. Sorry, that's not what I wanted to do. Just wanted a shell. So a set is a set definition.
We can't see the Python shell.
Sir, I think
Oh, sorry. Yes,
sharing
I'm
the
just
window.
sharing. I'm just sharing. Thank you for reminding me. I was just sharing Safari while I was waiting for the class to begin. So let's share the whole screen. All right, thank you. So here's a shell, and so a set is a collection, unordered collection, the two unordered collection. So rather it's a collection of unordered distinct elements or objects. objects, actually. If we're talking about Python, like in your math, you're going to say elements, or maybe even numbers if you really just want numbers. But in Python, we're going to say objects. So there are two adjectives, unordered and distinct. Unordered is the first time that we're going to be working with the collection where the elements are unordered. So we worked with strings. The characters, elements are characters and they are ordered. There's a first character, second character. We work with lists, elements are ordered, first element, second element. We've seen tuples, which are just immutable lists, elements are ordered, and so on. 2D lists, elements are ordered, meaning there is a first element, second element, and so on. You can ask, give me a first element, give me a second element, and so on. Here's how you create a list. Remember when you were a set. Remember when you're creating a list, you were telling Python that you're about to create a list by using square bracket, closing square bracket for strings, a quote, another quote, beginning and an end of a string. The way you're going to tell Python that you're going to create a set, well, with a little bit, well, we're going to get to it. Is an open curly brace, a close curly brace, and then put some elements in the set. So this creates a set, and as always, you can use a variable such that you can refer to that that element, that object again. In this case, set. Okay. So let's see, this is a set. If we ask Python, remember this type function tells you what type of object a variable S is referring to. It's telling you it's referring to an object of type set. And then you may wanna ask yourself next thing, what can I do with sets? Okay, so remember, if you really wanna know just in Python, what can you do with set? You can use a dir to ask what is, so what are the methods in set module that are available? One of the things you're going to see is, for example, add means you can add an element to a set. Then there is remove, you can remove elements from the set. This should tell you that sets are another example of immutable objects. So they can be changed, right? So unlike strings and integers and floats, and like lists, sets can be changed. They are mutable objects, so they behave like lists in terms of what's happening in memory and so on. Okay, so let's see what happens. For example, if I do help set, let's see how to use this add method. It's telling you it's a method. That means you call it with the dot operator. So if I want to add an element to a list, let's say 1,000. Let's see what happened. And we indeed see that 1,000 has been added to the list. Notice that it's added in some place out of your control. So that's because you really should not imagine that there is any order of these. In fact, when you were studying this in school, sets, and let's say when you're talking about sequences or lists, when you talk about sequence or list, you somehow assume some sort of linear order, that there's a first element, second element, that they're on the line, right? So a sequence or a list is something where elements come one after another. But when you were talking about sets, I hope you remember, you were using this blob, these diagrams where, let's say you take two sets and you want to know what an intersection is, you would drawing these two blobs with an intersection there. So when you look at this blob, typically you would put some elements in there, and from that it was clear that there is no order, right? You put randomly somehow elements without particular order in the blob. There is a reason why you're using the blob, because there's no order on those elements. Okay, so you cannot, when you're adding elements to an S, you cannot count, in which you cannot kind of, don't work with an assumption that you know where it's going to end up. Not only that, what are all the things that assume order? Whatever assumes some sort of order, you cannot do on sets. One of the things that is kind of, it's difficult to, at first, not difficult, I mean, you wouldn't even think of as assuming order, is indexing. But remember, indexes says, if you have a list L of 0 means give me first element, L of 1 gives me second element. So it may look like here 1,000 is the second element of that list. so that you can access it with S01, but you cannot index a set because there is no order. So you cannot ask me first element, second element, third element, because there's no order on the elements. So anything that assumes order, you cannot do on the sets, okay? But adding an element doesn't assume order. Removing an element, I can say remove a 2 from a set, it doesn't assume an order. Sorting assumes an order. You want to sort, if you want to sort elements of the set, you won't be able to do that, right? Unless you want to return a list that has the same numbers, but you won't be able to do that because sets are unordered objects. Okay, so those are the things that you cannot do. You cannot do anything that implies order. You cannot do slicing because slicing also assumes order, right? I'm asking, give me all the elements from the 5th to 10th position. That assumes order. Okay, but what you can do, you can add an element, you can remove an element, you can ask for intersection of 2 sets and so on. You can ask, is something in the set? So for example, we have this set S. I can ask, is 1000 in S? What about 1001 in S? We get that it's not there. Okay, so you can use in operator to ask if something is in the set. You can also loop through the elements of the set. So then the loop is just going to give you elements one by one, but you shouldn't again assume in which order it's going to loop through these elements. So for example, we can say for item in S, print item, right? So it's going to go through all the elements of the S and it's going to print them one by one. All right. Why are these sets? Is there anything else I want to show you before? Oh, yes, I wanted to show you one of the things that you had to do in assignment number 4 is to remove duplicates as part of something. You had to remove duplicates and you were not allowed to use sets and dictionaries. So you're going to see now one of the reasons I didn't want you to use it, because somehow magically sets do the work for you. I wanted you to know how to detect duplicates, how to remove them, and so on, okay, so that you find your own solution. But by the definition, remember that throughout the semester, we have seen these special functions that, in fact, for example, if a function has exactly the same name as an object type in Python, for example, int, that function is always going to try to produce an integer. Okay, so if you give int function string that looks like an integer, it's going to try to produce an integer. If you give it a number, it's going to try to kind of convert that whatever number is into an integer and so on. We have seen a similar thing with lists. So lists are object and we have these functions that have the same name. And this function always try to, whatever you give it, try, if it's at all meaningful, to create a list out of it. So for example, range function, if we do range 10, that function produces a sequence of numbers 0 to 9 inclusively. So list is going to convert that into a list, okay? So these functions, these so-called constructors, these functions have a name, they're called constructors. And we're going to learn exactly what constructors are in the next class when we start objects. So these are the functions that try to construct an object of that type. So we have seen int, we have seen float, we have seen list, we have seen str. If you give it a number, it's going to create a string that looks like that number. Okay, so this one creates strings, lists, integers, floats, and so on. Of course, there's a function that there is equally constructor or special function that tries to create a set from whatever you give it. Okay, so if I have a list, so let me actually store this. Okay, so I have this list, and maybe I can do list append 8 L append 5, append 8 again, append, I don't know, 8 again, append 9, 8 again, and I append 9. Okay, so we have a list now where we have some duplicates. We have, I know, 4 8s and 2 9s and so on. So if you give to remember what these constructors do, from whatever you give them, they're going to try to make a reasonable object of type set from what you give it. So if you give it a list, what it's going to do is just going to convert that list into a set. But remember, sets are not allowed to have duplicates. So this simply is going to remove duplicates, which was what you had to code for your assignment. And although your result had to be a list, but now that you have a set, you can then convert a set back to a list. So if you do list set L, so first this is going to create a set. Taking list L, this set is not going to have duplicates, then you take that set and convert it to a list, and you get a list with no duplicates. Okay, so magically, by somebody else's work and code, this, when you convert something to a set, it removes duplicates. By the way, it reminds me of, so we were working with a set like this. You may wonder what happens if you do add, and now I try to add, I don't know, 2 again. So whoever coded this add function had 2 things as a choice, because you don't want to add 2, right? Because if you add 2, it's not a set anymore. You have duplicates, right? And that breaks the definition of a set. So you have 2 courses of action that you can code. One is that you throw an exception, right? You can have a crash, says 2 is already there, you cannot add a, so that's kind of allowed, dealing with the problem in a loud way, right? You throw an exception. The other one is basically that you have a silent handling, right? So, you know, nothing crashes, but you as a programmer better know that 2 was not added, okay? So, so it's somehow, so if you look at this, it looks like it didn't crash. So this is handled in silent way by Python, but 2 is not added. It just ignores this because you cannot add 2, sets cannot have duplicates. Okay, so why would you care about sets? Oh, by the way, just like everything in Python, really there is no, you can mix data types, so you can add anything. So an element can be, oh, wrong syntax, because what I want to add, I'm making a function call. I have to use parentheses for function call, not a set. So I added a single string to my set. So now my set has whatever 4 elements in a string. It can have, it's a mix of any object. So set is a collection of objects in Python in a literal word. Okay. So you may wonder, why do we care about these sets? They seem to be able to do everything. I mean, lists seem to be able to do everything that sets can, and more. They have order, I can sort them, I can ask for the first element, and so on. Okay, so here's why. So let's see what we know about sets. If you are interested in, when you're designing your solution, somebody asks you to code something, or you want to code something, you hopefully, once you figure out what you want to do, you're going to have some idea what you are required, what type of operations you're going to require to be repeatedly doing. And if your operations only involve adding, removing, and searching, then sets are for you. So let's see why. So let's see, if you have a list, even if it's a sorted list. So let's remind ourselves, how much do these operations cost you if you do them on a list? So in an unordered list, adding an element to a list, adding or appending. So let's say we use append to add an element to a list. It really just add it to the end. That's a constant. I'm indicating O of 1. Big O of 1 means constant number operation. That's like really just a constant. Think of it, you can do it as in one operation. That's what 1 stands for. Adding an element is 1. Removing an element is O of n. I think I already explained this. If you have to remove an element from the middle of the list, elements in the list have to be consecutive. That means that hidden behind the removal of an element is moving half of the elements, such that the elements in the list are now consecutive, and that's O of n. Removing in the list is O of n, and doing in, so searching, doing an in operator, that's a linear search in Python, and anything else you can do better. So we are doing linear number operations. So If you want to be removing and searching unordered list, you are doing linear number operations, so not so great. Okay, in a sorted list, again, if you want to add an element, right, you want it to stay sorted. So when you code it, it still may cost you O of n. Let's say you want to add it, and it turns out it has to go in the middle of the sorted list. So this may take you O of n. So adding is O of n. Removing is equally O of n, because you may be removing something from the middle of the list. Removing is O of n. But searching, we have seen that you can do searching by doing binary search. So searching is O of log n. Okay, so at least much better than an ordered list. So let me tell you what is that in the sets. Adding an element to the set is constant number operation. So think of it as one operation. Removing element from a set is one operation. And finally, searching, so doing in. So doing in on a set, it's one operation, okay? So I will ask you for the sets, and basically it's the same in the dictionary that we're gonna do in the second half of the class. So I will ask you that for now, not for now, basically until your second year, or unless you wanna do your own studies, you take this as a black box. You take it as I told you that adding an element to a set, removing an element of a set, and searching for an element of the set, that's a constant, okay? So that you're going to learn why. So the analysis of that and what is the tool to use to achieve that. Technique is a data structure. There's a special data structure that is designed and used for that. So you're going to have to learn about the data structure, and technique is called hashing. And to do analysis, understand why is this constant time, you will need to know some more mathematical tools, including basically this is actually randomized number operation is content in the randomized model. So you should study and pay attention to probability, because in computer science, some of the best algorithms are actually based on, are randomized, that they use some probabilistic principles. So they use some randomizing, and then you need to know probability to understand why it's working well or not. But for now, take it as just a black box. The same way I told you the best sorting takes n times log n times, I mean, number of operations, n times log n for sorting. Take it for the sets. Adding, removing, searching is constant. Okay, instantaneous, meaning if you have million elements, it's a constant. If you have billion elements, it's still the same constant, okay? Billion, 100 billion, is still a constant operation. Think of it as one operation. Okay, so now you may ask the opposite of the previous question. You may ask, oh my God, but these sets are way better than these lists. Why would you ever use a list? Okay, so I have two answers for that. First of all, when you are saying that one thing is better than another, you really have to be sure what type of model of computation are we talking about. And even that, you're going to learn in your second years what are the model of computations. And by the way, data structures, analysis, and hashing, everything that is between sets and hashing, you're going to learn in your second year data structures and algorithm course. That's really when computer science starts, like serious sciencey stuff. So what I wanted to say is that, let's say, so ignore this unordered list. You shouldn't keep things unordered. So when you look at a sorted list, it says that searching is log n on a sorted list. We learned that last time how to do it. And here that you can do it with constant number operation. Constant is way better than log n. Even though log n is a slow growing function, it still depends on n. So as n grows, your number of operation grows. And you would say, okay, clearly that the sets are better. But actually, we are not exactly talking about same model of computation in a sense that if all you are allowed to do are comparisons, like if you're looking at a model of computation where all you're allowed to do is compare elements, say, are these two elements are the same? Are the or this one is bigger and this one is smaller. If this is all you have to do as a model of computation, then you can actually not do better than log n. Okay, log n is an optimal solution for searching in a model where your operations are basically comparison based. Okay, so actually hashing uses something more than just comparison to achieve this running time. That's number one. So when we're comparing things, we better understand what we're comparing. Are we comparing things that are working in the same model of computation? And even model of computation, I didn't explain what it is. It's outside of the scope of this class. But let me get to the second part. Even if you don't understand what model of computation means, it really depends what you need. Here, let me give you an example of things that sets do very badly. So if you have, let's say you have a big sorted, you have elements such as 1, 50, what do I want here? 57, 80, 100, 120, 345, and so on. So let's say these are our elements, and I want to ask not just is, let's say, 110 there. I want to ask, is 110 there? We know that sets are very fast to tell you yes or no. But in addition to telling me is 110 there, I want, and this is needed very, very often for many applications, I want that if 110 is not there, that you tell me basically what is the closest element before it in a sorted order, right? So I would want in this collection, what's the closest element to what I'm looking for? This is so-called predecessor. Closest but smaller than me is predecessor, closest but bigger than me is ancestor. So, or successor, sorry. So predecessor and successor. So in addition, I want to know what's a predecessor. So for 110, predecessor is 100, is the closest element to what I'm looking for, 110. But smaller than me, and 120 successor, it comes right under 110. So in binary search, so if you have a sorted list, when you're doing binary search, you can actually also in log n time tell somebody exactly, even if 110 is not there, you just look to your right or where you ended up on that list and report where's the element that you got stuck. You get a predecessor and successor. So in sorted list, you can answer predecessor queries, questions, also in log n time, but in sets and dictionaries, it takes you linear time. You basically have to look at all the elements before you can report that, okay? So for things so it really depends what you're gonna be solving. All right, so now that I told you what sets are used for, so keep them in mind when you're solving your problems. If all you really want is to add some element, so you building something you wanna add, delete, and ask, is it there? Then use sets, okay? So let's code something with sets. So you had in your assignment number 4, previous assignment, you had to work with dictionaries of English, like with the dictionary of English words. And you had to analyze something in particular. You had to find all the, I forgot what. Oh yeah, it was for the game of Scrabble. You had to find all the words that you can create, anonyms or whatever the word was. Okay, so so let me show you. So we're going to do something similar, and we're going to see what sets are very useful for. All right, so first of all, I want to tell you that basically all of you are running a spell check. When you are using something on your computer typing, it's many of the applications are using a dictionary. So somewhere hidden on your computer, there is a dictionary in your operating system. So for those of you who have Linux machines, and for those of you who have Mac, which are actually based on like Linux kernels, I can tell you where this dictionary is in the operating system. So basically it's here. The location is /user/share/dict/words. So words is a text file containing basically all the words in English language. Well, all the words that you assume to be using, right? That you need for spell checking and I don't know what not. A command less in Linux just lists the file. So you can see actually this is a dictionary of English language is there on your computer. So what we're going to do first, we're going to open this file and we're going to convert it to something that, like we did before, is something that's easier for us to work with. So for example, first thing I want to do is, given all the words of English language, I want to find all the palindromes. Okay, so what are all the English words that are palindromes? So first of all, so for that I will need a dictionary, but we will get to what a palindrome is for those who don't know. But let me show you, and we've seen this before. I have a starting code. All right, so you can open that dictionary. So ignore this for now. So you know how to open a file. You now do open and you just put a whole path of where that file is. Then I want to read it. Then I want to convert all the words to lowercase, right? I'm just really interested in words, not whether they are kind of you have capital letters or not. And then I split it. You've seen that in each line you have a new word, so I can split it. And the result of this, so let's run this. And the result of this should be familiar. It's basically a list of strings where each string is a word from that dictionary. So if I do word list, so we have a list, I can ask, give me first 50 elements of that list, and it's showing me what it is. So these are the words from that dictionary. Obviously, they are all starting with A. You can also see, oh, I want to know how many words this dictionary has. And it has roughly 236,000 words. By the way, I didn't give you this dictionary for your assignment number 4. There is a reason for that. And the reason that it would be way too slow for what you were doing, for the tools that you have seen. So basically, I looked for truncated dictionary. So I think the dictionary that you worked with had about 60,000 words. I found one 60,000 words because if your concern was just a correct implementation using list, you would end up waiting way too long. But right now we're going to use a full English dictionary. Okay, so we see now that we have a list of strings and each string is a word from English dictionary, where we have about 236,000 words. Okay. That's what that line was saying. Okay, the number of words in English dictionary is whatever length of that thing. Okay, so I want to find all the palindromes in English language, or at least among the words that are in my dictionary, in my English dictionary. Okay, so what's a palindrome? Can somebody tell me what's a palindrome? I'm going to take a sip of water while waiting.
Isn't it a word like when you write it backward or forward, it's going to be the same?
Exactly. So a word is a palindrome if when you read it from left to right and when you read it from right to left, you get the same word. So an easy example is, for example, a name Anna. You read it from the left, it's Anna. You read it from the right, it's Anna. What else would be a good example? I don't know. I'm sure there are many examples. We'll come up with some more. So what we want to go is to go through the words in English dictionary and report all of those that are palindromes. Okay, so let's code that. So we can do that quickly. And let's see what's happening. So def palindromes, let's say palindromes. Let me try to spell correctly, palindromes. Okay, let's say input to my function palindromes, it's a list of strings where each string is a word from English dictionary. And what do we want to return? Let's say I want to return also a list of strings, but this list will be returns list of all palindromes in English. Okay. All right. So to solve this, what do? I want to create a list of palindromes. So the way to do it is I have my list of words. Okay, so I want to go through this list of words, my dictionary. I go through my list of words. I take word by word. I test each word. Are you palindrome? If it is, I add it to the list of palindromes. Otherwise, I just take the next word from the list of words. So let's code that. So in the beginning, what do I have here? Palindrome. Okay, let me just call it pal. In the beginning, my list of palindromes is empty. And then I go through the words in words. So I pick a first word from the list of words. And so for each word W, I need to test if W is palindrome. We're going to see how to test that. But if it is a palindrome, then if it is a palindrome, then we just add it to the list of palindromes. So I append word W to the palindrome. Okay, otherwise, there's nothing to do actually. Otherwise, so we just take a next word. All right, so once we go through all the words, so once we are done with the loop, we go through all the words in the dictionary with return return list of palindromes. Okay, so if we want to know, let's say, so let's say in the main here, I want to really call this list of palindrome. I want to pass it my list of words of English language, and I want to store that in this palindrome list, and I want to see really, I want to find out what are all the palindromes of English language. Okay, so the only thing that remains in this code, unless I made mistakes, is to figure this out. How do I test if this particular word, so we pick a word, so in our case, the first one will be A. Well, A is actually palindrome. It reads the same from beginning and in front, but you know, at some point it's going to pick a word like this, A, B, A, M, A. And you know, it needs to test is that word is a palindrome, and in this case it's not, so it should return false. So how do we test if a given word is a palindrome? And actually Python is particularly nice for that. There is an easy way to test if a word is a palindrome. So how do we do it? How would I test if a word W is a palindrome? Anybody?
Can you reverse the string and check if is the same thing?
Exactly. So so basically to test if the word is palindrome, you just reverse it and see if the strings are the same. So for example, this one here, this word, ABAFF, you would test, is it equal to FFABA? Well, obviously not, so you will get false, but if you have words like this, ABBA, when you reverse it, you also get ABBA, so we get true. So all you have to do is you're asking, is the word W equal to the reversal of W? In Python, we've already learned is there is a very nice slicing way to reverse a word. So you basically use slicing with -1 step. So you go from beginning to the end, but actually you go by putting -1 here, you indicated that you are reading this string from the back. Okay, so this reverses the string, and you're asking, did we get the same string? So that's it. We solved this problem. Let's see what we get. And so far, there was no new tools that we use. So let's see what are the palindromes that we get. Len of pal, 100. So there's about 197 palindromes in English. What are the examples? This is the one that surprised me in the previous class when I did this. Civic. It's not something that we get. So civic reads the same from front and back. And I don't know, some other ones that I don't know what they mean. Pop reads the same. That one I know, but pop, I don't know what this is. Anyway, so these are the example. Of course, all the single letters that are considered words for whatever reason. I'm not sure why would C be considered a word. Well, we actually have some duplicates here, so we could be removing duplicates. Okay, so we have in fact 197 less than 197. We can convert this to a set and see actually how many distinct palindromes there are. But right now that's not what I want to do. What I want to do next actually is find out what are all the anonyms in English language. So what's an anonym? But no, before preparing this lecture, I think last year or 2 years ago, I was teaching, I added this lecture to my repertoire. I didn't know what anonym is. I was looking for good things, applications. So it's no surprise. I really didn't know what it is, but maybe some of you know. What is an anonym? So here's what anonym is. I want all the anonyms in English language. So an anonym palindrome is a word such that its reversal is equal to the given word. Okay, so a word and its reversal are the same. That's a palindrome. Anonym is a word such that its reversal, it's a word of English language. So there's nothing to say that they have to be that word and its reversal have to be the same. What you want is that a word, given word, and its reversal is also in the English dictionary, right? So when you reverse a word, you want to make sure that the word, that it's an actual word and not some nonsense, right? So for example, all the palindromes are anonyms, right? Because if dad, if you take a word from English language like a dad and you reverse it and you also get a dad, well, that means that the reversal is also in English language because the original and the reversal are the same, okay? So all the palindromes are anonyms, but not the other way around. So we're gonna find some examples once we code it. So what we wanna test is if the reversal is also in the dictionary, if the reversal is also the word in English language. Okay, so let's code that. It should be exactly the same code, right? Except for like one line will change. Well, I'm going to change the variable name. Let me call this Anna for anonyms, for W in words. Okay, so this I'm collecting anonyms. I'm collecting anonyms, and I'm going to call here. I want to know what are the anonyms in English language. So I'm going to call this function. I guess I should call it by plural because surely there's more than one on the list of English words. So I want to know what that is. Okay, so the only difference should be, so to compute anonyms, everything is the same as before. I go through the words of English language one by one. Each time I take a word W, I want to test if W is an anonym. So to test that, the definition is you are an anonym if your reversal, and we know how to compute reversal in Python particularly easily, if the reversal of word W is in the dictionary. So we go and test, is this also the word in English language, which you just ask, well, is that word, is it in the dictionary? Is it in the list of words? Okay, so let's run it. Okay, so I run this and it's standing there. You may say, okay, maybe it's going to finish any moment now. All right, let's see. While it's doing it, let's try to use our brain and figure out actually how long we're going to wait for this. And in fact, why is this seem to be so much slower? It's still running. This was instantaneous. And the code looked basically the same. The only thing we changed, we replaced this with this. Okay, so let's do the analysis of palindrome solution. So if this list words has n elements, so in our case we know, since we're passing it word list, we know that this list of words has about 260,000 elements. So on a list of n elements, the palindrome function, how many operations does it do in terms of big O notation?
N.
It does n operation. So this is one operation. This loop is executed n times, and each time you just pick one word from a list. So you execute n time, and every time you execute it, you do one operation. So I don't even need big O for this. This time, so this line here, every time you execute this line, you take a string, you reverse it, and you do the comparison. You may say, exact thing to say, how many operation is this? When you execute it once, when you execute that line once, would be, oh, you take the length of the string, you're comparing this character with this with this, this with this. But the words in English language, there is what? Is there even a word of 20 characters? I'm not sure. So probably the longest word has at most 20 characters. So that's for us constant number operations. That's like 20 operations, or maybe reversal is, I don't know, 20, and then comparison another 20, that's 40. That's so it's at most 40 operation for any word of English language. So that for us is a constant. So we're going to put O of 1. So big O of 1. So it's for a constant number of operation, but we execute this line n times. So we have n times 1. So this cost us n. Adding elements to the list. We do this at most n times. And this just returning something. It's O of 1 because we basically return the beginning of the list. So this is n plus n plus n. So this is roughly 3n plus 2. When we remove the constant, we get that this is linear. Okay, this analysis, this is still running. Let's look at this one here. Everything is the same except for that one line. This is the same. I only changed one line, so I'm going to get to that line. Okay. This line. So here we said we compare two strings, but we know that these strings are short, less than some constant, let's say constant 20. So that's constant number of operations. Here we have a string. We're asking, is this string in this list? So when I execute this line once, how many operations am I doing? Remember, in does a linear search on a list. So words is a list. It has an element. And in does linear search. We have seen this last week. So we are asking, is this word in this list? How many operations is that if the list has n elements?
N square time.
Well, in total. So when I execute this line once, I do n operation. But I actually execute it. But this line, every time you execute this line, you do n operation. And the line is executed n times. So we get that the number of operation is n times n. So that's n squared. So when we add all of this up, we get 1 plus 1, that's 2. We get 2 plus 2n plus n squared. So we get n squared plus 2n. This is roughly plus 2. You know that you remove constants, so this disappears, and you end up with n squared plus n, but n squared is way more than n. It dominates, so you keep the fastest growing term, and you get O of n squared. So this one does at least n squared operations. So I'm gonna get you, Aid. So I'm going to stop this, and I'm going to tell you how long we would have been waiting. The dictionary has, what was it? Len of words. It has, no, word list, about 236, was it? Word list is 236. So let's do 236,000 squared operations. So it does this many operations, but this doesn't tell us much. But let's say that you have a very good computer. You can do million Python operations a second. So that's 1, 2, 3, 1, 2, 3. So that is 55,000 seconds. We still have somehow don't have a good feeling. How much is 55 seconds? Well, divided by 60. We're going to get minutes. It's already now looking bad. 928 minutes. Okay, how many hours is that? So you would end up waiting more than 15 hours to get that solution. Okay, so let's look at this solution. What is it that costs us here a lot? Is that inside of the loop, we are testing if something is in the, we're repeatedly asking, is this in this collection? Is this in this collection? And we've learned that in particular, this list of words was not sorted. So we weren't even doing binary search. If at least we were doing binary search, but then we would have an after extra permutation, it would be n times log n. But instead, we just learned that if you just want to be checking if something is in a collection, we should use sets. So I'm just going to change. So instead of using these words list, I'm going to create from that list, I'm going to use Python's constructor, a set constructor, to convert that a list of words into a set of words, okay, SW for set of words. And instead of testing or word set or set words, no, word set. And I'm going to now, instead of testing, is the word in a list words, I'm going to test, is it in set words? So let's see now how fast our solution runs, and it's over. We didn't even blink, right? We're still calling that function. We didn't blink. And let's look at that function. It has too many numbers. Let's see how many anonyms there are in English language. It looks like it's about 1,400. Let's look at some of them. Let's look at 100th to 150th. So there they are. For example, words. What would be something that we can recognize? Animal, lamina. Lamina is apparently also a word in English. Let me see something. I want to find some good example of an anonym. I think I managed. Let me see. Anna, 200 to 250. Doesn't matter. I don't see anything nice.
The second word.
Which one? Bats and stab. Oh yeah, bats and stab. That's a good one. Yeah, that we all know. I mean, because usually the word in reversal, I don't even know it. Anyways, bats and stab. It's a good one. Thank you. All right, Maid, quickly. I want to show you dictionaries.
I didn't understand why the first anonyms was big O of n squared.
Because we had this. Okay, so when you execute this, forget the loop. When you execute this line once, and you just call it once, you are asking, is something, let's say an element, in the list? That is linear number operation. The way Python implements in on a list is a linear search. You mean you have to read, so words is a list. It has 236,000 elements. You will have to check every single one of them to see if the word is there. So when you execute that line once, you're going to do n operations. But in fact, we don't execute it once. We execute it n times because we do it for every words of the list words. So that's why it's n times n, it's n squared.
But didn't we count the n in the for loop? Like we already counted how many times will it repeat?
Here, the loop is executed n times, but every time here, the loop, this line, I'm asking how many operations does this line cost you? How many times do you execute this line? N times. Every time you execute it, you do n operations because in linear search, this costs you n operations. So the number of operations that this line costs you is n squared. You execute it n times, and each time it costs you n operations. N squared.
Thanks.
But that was when words, but in a set, you still execute this line n times, but we are doing in on a set. That's a constant number of operations. So in a so when WS is a set, this is constant number of operations, and you do this line n times. So this is now O of n rather than O of n squared. So you get n, and 2, so 3n plus 2. That is now linear if you're using sets. That's why it was instantaneous on this example. Okay, I have to show you dictionaries. So dictionaries are like sets plus. What do I mean by that? So here you can do also unordered objects, also mutable, but in addition to having, in addition to having keys that you're looking for. So you can think of this as in a set, when you're looking for something, you can say, I'm looking for a key. In addition to keys, each key may be associated with more data. What's an easy example of that is, for example, that student numbers. Somebody may say, okay, first of all, what I want you to do is, if I give you a collection of student numbers, I want your program to first of all quickly tell me, is the student number there? So somebody gives you 300123456. Okay, is this number there? Meaning, is this a student number of a student registered at University of whatever? Okay, I want this done quickly. You should say, okay, you should put all the student numbers in a set. And then when you ask me if the student number is there, I can do that super quickly. But then the person say, okay, yeah, wait a minute, but this is just the first step. First of all, I want you to tell me if the student number is there. But the next thing I want to tell me, if the student is there, of course, I want all this information about the students, maybe their grades and I don't know what year they're in or something. So with each key, in this case, key is a student number, I want some data associated with it. This is what dictionaries are for, okay? So you're going to search a data based on the key, and you're going to use that key to access the data. The syntax looks a little bit like a list. So in a list, -2, 3, 3.5. So in a list, remember, you access the data by giving a key, which is just an index of a position, right? You can think of that as a key, that if somebody tells you, give me a second element, you just do, okay, I'm going to give you the key for the second element is position of that element, is a, you know, its index is a 1. So you get a quick access to a data in the list if you know its position in the list. So the keys are positions in the list when it comes to the list, right? So if I do this one, this is going to give me access to the last element in this list in this case. Okay, for the dictionaries, it's very similar, except that the way the syntax is very similar, except that the way you access the element, it's not an index, it's the keyword that you're looking for. In the case of my example that I gave you, with the student number, the keys would be student numbers. So what I would like to do is, if I have a dictionary, and by the way, that data type in English, in Python, is called dictionaries. It has nothing to do with dictionaries of English language. It's just a data type that's called dictionaries. Okay, so what I would like, if I have a dictionary D, I would like to say use as an index. Let's say in that example, I would like to use as an index a student number, such that if I press enter, it gives me information about the students. Okay, all right. So how do you create a dictionary? First of all, it's very simple. You can create an empty dictionary. It's a bit confusing in Python because both dictionaries and sets, because in fact they're very related, what you have on your keys in a dictionary is actually implemented as a set. So if you want, they both use curly braces. So if you want to create an empty dictionary or a set, you would think, okay, in both cases, I'm going to use curly braces. And then you say, wait a minute, but which one does it create? Is this now an empty dictionary or an empty set? By default, Python, actually, you can ask Python, what did you just create? And it says, I created a dictionary. If you wanted to create an empty set, you can just call a constructor without giving it anything. So this now is an empty set. Okay, and D is an empty dictionary. Okay, so let's say what I want is I want to create a dictionary where the keys are the stock symbols of companies, and associated with every stock symbol is the full name of the company. Okay, so I have D, and how do I do that? So what do I want? A key. So instead of having here an index, instead of saying, as in a list, I want L of 0 to be blah, you're saying you use a key that you want for the dictionary. You want to say, I want to use a stock symbol as a key, and then the data. So instead of using an index, you're going to use a key that you want. And the index is going to be a full name of the company. It's just a silly name. Python, Apple Inc. All right, so what's another one? So let's see what we have now. Right now, our dictionary has one element, and you access it by the key APPL. I can add another one. The key is, let's see which company I know, a stock symbol, and the name is, I think, Google Inc., or there is an app. I don't know if this is from. Okay, so now a dictionary has two elements. Again, elements are separated by commas, and the keys that you're using to index those elements are, again, they're stock symbols of companies. Just like in a set, you can ask, is the key is there? You can ask APPL, although it maybe in reality is AAPL, but it doesn't really matter. Is APPL in my dictionary? Sorry, I didn't finish this string. And it tells you true, it is. That key is in there. GOG is in there. Or if I ask something, telling me that one is not there. So, and if I want to access the data associated with that key, I just use that key as an index, and it's telling me, okay, at that index you have this data. So based on this, basically, and I'm not going to code this, I code the little thing where I have a file with all of these stock symbols of companies on NASDAQ, and I created a dictionary containing all of this information. I'm going to share it with you, but really I'm not going to go through it. It's too simple for what we're doing. I'm going to quote something else, but you're going to find it in Brightspace right here. That's where I populated this dictionary, doing exactly what we just did with the data from the companies that are listed on NASDAQ by opening this company, and so on. So then we get a bigger dictionary than what I just did. It's too big, it squeezes too many lines, but you can see, you can ask, for example, is now in D, is it in D now? I don't remember, it is, and I can then ask, okay, tell me for that key, what's an actual name of that company? And it's telling you that it's Yahoo Inc. and it's common stock, whatever that means. Okay, so I'll share that. But what I want to do until the end of the file, I want to use dictionaries for something that we already seen. But in this particular case, I want to analyze, I basically want to do what's called data mining. I want to take something like a book, and I want to learn something about the particular author by analyzing what type of words they use, what are the most common words they used, how big is their vocabulary, and so on. So the book is in a text format. I picked a book. There is a webpage, by the way, that you should maybe know about. It's called Gutenberg Project, and it takes you to gutenberg.org if you type that in Google, and there you're going to find basically 60,000 free books. So these are the books that are not anymore under copyright. I believe for the books, the copyright is, I don't know, 60, 70, 80 years. So once enough years passes, the books are now free, and you can find them on, obviously they will be old, more than 90 years old. So the book I picked is was like an entertainment book from 1800s, 1845. It was written, first appeared 1845 to 1847. It's called Varney the Vampire. The book has 876 double column pages, 232 chapters, and it looks like it's written by two authors. Obviously, it seems to be about vampires. So let's learn something about this book by just mining the data before even reading the book. It seems to be too long. Okay, so what I'm going to do first, I have prepared some of this, just opening of the file. Just a moment. I need to first close this. This is some bug that happened with my idle. I'm too lazy to. Okay, so forget this for now. This part, we did this in previous lecture. I'm going to put it there so we don't look at it. So all this does, it opens the book, it reads it, puts all the letters in lowercase, splits it on white spaces, and goes through, removes punctuation and stuff that you already had to do and learned. And at the end, what you end up with here, if I run it, what I end up with is a list of strings, basically, it took a couple of seconds, containing the whole book. So let's see, a book is now a list of strings, and it really, strings are in order, they are in the book, right? So let's see how many words does this book have. It has 332,000 words. The book has 332,000 words. Let's see some of the passages of the book. I can say, okay, this is a list. So give me what appears from 5,000 to 5,050th word in the book. And we have something, man in the corridor when first the screams of the young girl awakened alarm. And oh, okay, let me not continue reading. So that's the, so what's in the book is a text of the whole book, word by word. One of the first things you may want to know, how rich is vocabulary of this person, in this case, actually these two authors who wrote the book. Okay, so how do you know the vocabulary? Well, I want how many different words they're using. What that means, I want to create a set. You can just create a set, it's going to remove the duplicates. And if you look at the length of that set, it's going to tell you how many distinct words is this author using. So let's do that. So I'm going to convert this book to a set. And I'm going to ask, okay, what's the length of that set? So that's going to tell me how many distinct words are these author using. They're using about 1,500. They're using about 1,500 words. I did the same, actually. I downloaded on this webpage. I did the same for War and Peace by Tolstoy. Oh, but the Python is not going to let me. Anyways, if you just download another book like in War and Peace, and you want to know how many words, distinct words, what's the vocabulary size of Leo Tolstoy, I got about 21,000. So that's already one measure. You can say it's not an absolute measure like any number, but it's telling you something. You know, in his War and Peace book, Leo Tolstoy is using about 6,000 words more than it's used in this vampire book. All right, but what I really wanted to know now, I want to know more details. So I want to know, for example, what are the most common words that the authors that are in this book? Okay, it should give me even some idea what the book may be about. So what we want to do is frequency counting. So we already done that, right? So given a list of strings, I want to know how many times each string appears. So we've done this. All right, so we've done this in one of our previous lectures. So I can just use that code and see how it goes. So remember, in the previous class, what this did is maybe 2 classes ago, we did a frequency classes, a list of strings where those strings were cities, and we counted how many times each city appeared. And we returned a 2D list where we had this string where elements were lists of size 2. First element was in a list of size 2 was a city. Second one is how many times this city appears. So first element is a string, and second element is telling you how many times that string appears. So this is exactly this solution here. Okay, so we coded this already, so we might as well use it. So we have a frequency. I want to call it on my book, and I want to get the result F for the frequency counting. So this should return me a 2D list telling me for each word in this book how many times it appears. Okay, so I pass the book here, and I press run. Okay, it's running. It's there, it's running, it's running. Okay. Before we discuss this, how long it's going to be running and stuff, let's figure out, can we solve this differently? Okay, so what do we want to do? What we want is that I have this book, a big list containing individual words from the whole book. So strings, each string is a word from book. So what I want to, let's see what we want to compute, what we want to do. So I want to go through this book word by word. I take a word and I want to know how many times this word appeared. Okay, so that means each time I take a word, so far I'm keeping somewhere some collection where I need to see, is this word, have I already counted this word? So I need to test, is this word already in the collection? Or if it's not, then I add that word with the count 1. If it is, I find that word and increase its counter by 1. So this description should tell you what are the operations that we're going to be doing in this solution. I need to test is word I just picked, is it in the collection? Okay, I need to test is this word in a collection? Okay. So whatever collection I'm using, this better be my keyword, right? A word that I just picked should be my keyword because I need to keep on looking for that word. Okay, so, and with each word, I need to have associated a counter. So we have seen that if you want, what is the operation that we keep on repeating? This is testing if a word is in some collection. So that tell you what collection should I use? In which type of collection is it cheap to test if the element is in that collection? Well, that's set or dictionaries. So what should I use, set or dictionary? Well, is it only words that I'm looking for? Or is there something associated with these words in this collection? The answer is I want something associated with each word, which is with each word, I want associated counter. So that should tell you I should use a dictionary where my keys in the dictionary, like Python dictionary, where the keys in the dictionary are words in English language, and associated with each key, so with each word, is the number of times, not words in English language, words from the book. And associated with each key is how many times that word appeared in the book. So let's code that, okay? While this one is still working, the old solution with 2Ds, let's code frequency via dictionaries. Frequency using dictionaries. Okay, so I have a input is again is a list of words. Actually, or book. No, input. I'm going to use a book because it's more meaningful name here. So input is a book. So input is a list of strings, which is my book, and output is going to be my collection. I decided the way I'm going to present you frequency counting from this book is going to be dictionary. So it's a dictionary. Okay. So since what I want to create is a dictionary, I might as well start, before I even look at anything, I start with an empty dictionary. So what did we then say how I want my solution to work? I go through the words of the book one by one. Okay, so that means I need a loop, I go through the words of the book one by one. Okay, now that I have an individual word, I want to test, is that word already in my, or maybe I should use here not D for dictionary, but freq for frequency. I want to know, because that's where I'm going to be storing my frequency count. I want to know if this word, is it already a key in my dictionary? That would mean that I already found it, right? The counter is already there. So all I'm testing, and we know that all we have to do is then ask, is this key in the dictionary? Ask if word is in the dictionary frequency. Okay, if it is, all I have to do, remember, how do you access data associated with a key? It's the name of the dictionary, is frequency. You give it a key. Key is a word, right? Not an index now. Key is a word. So go to that word in the dictionary. And so what frequency of word, remember when you're accessing a dictionary with a given keyword is going to give you data associated with it. So frequency word actually is the number of times that element already appeared. So you're going to take that, it's an integer, we're going to add 1 to it, and that's going to be a new number associated with that key. So frequency word gives us back the number that is associated to that key. So we increase it by 1. Otherwise, if that keyword, if that key is not in the dictionary yet, it's not in my frequency count dictionary, well, I add it. And we know how to do it. We saw this with this Yahoo tickers and stuff like this. I take that key, and I just associate a value with it by assigning to it. Okay, so this is when first time you find a word, you just set it to 1. Okay, the value associated with that word. And that's it. Hopefully you see that this is actually much more, not only you're going to see that it's incomparably faster, you're going to see that this is, it's much simpler, right? So once we are done with this, you just return the dictionary. So let's see, this one is still running. Okay, if you're wondering how long you would have waited for this one, we actually done, I hope we've done analysis when we done this. So basically it's roughly n squared times, but now n is even bigger than when we were working with dictionary. This book has more than 300,000 words. We would have waited even more than 15 hours for that solution. So let's instead call this one, the one using dictionaries. So let's use the dictionary solution. Let's run it. And there it is, couple of seconds, we are done. So let's see what we have. So we have this F is now a dictionary. It's too big for us to, list it, but I can ask, for example, here's a word I'm guessing appears a lot, D. Oh yes, it appears 17,000 times. What else? This book is about vampire. So let's see how many times the word vampire appears. Only 18 times. It's such a long book. So first time I looked for this, I was very surprised by this, but it turns out in 1800s, that's an alternative way that they were spelling vampire. And now you see there's 491 times the word vampire appears, and so on. By the way, you may now wonder, okay, but I really want to know what are the words that appear the maximum number of times. And then you may say, oh, okay, just sort. And you're going to say, you know, you sort from largest to smallest. So sort from smallest to largest in reverse. But remember, this is a dictionary. You cannot sort. So if you really want to sort, once you are done, created a dictionary, if you still want to analyze, do some sorting, then you better convert it then to a list. You can't really do this list F. You can, but you're not going to get what you want. Because remember, in a dictionary, you have keys and you have data. So which one is it going to sort? Which one is it going to convert to a list? It turns out it only really converts to a list, I think. It only converts keys to the list. But that's not, our keys are just words. We want also the counts. Okay, so for that reason, so this one does convert it to a list. And it only then has not F, sorry, we cannot slice F. F is a dictionary. I didn't save the list. But so basically you can write a little code that translates this to the 2D list containing all the information that you want. So I'm going to, wait a second. I'm going to quit this. So I hope I didn't change this one. No. Okay, so here I wrote a little code that turns this into a list such that the list contains all the information I want. That it's going to contain these tuples with 2 elements, with a count and a string, with count being first. So when I'm sorted, it's going to be sorted by the first element, which is a count. So if I run it, so we are done. This is a dictionary. And then I call my own function to convert it to a 2D list. So let's see what are the first, let's say 30 elements in that list. You see that there are tuples with the counts. D appears 70,000 times, project 91 times, by appears 1,300 times, but this is not sorted. So let me sort this list to see which word appear the most and repeat this slicing. Oh, but it's now showing me all the list words that appear only once. That's because I'm sorted from smallest to largest. I better reverse this because I want from largest to largest number to smallest. Okay, and now I can see, okay, so what are the 50 most common words in this book? All right, so unsurprisingly, they are words that really don't have anything specific to do with the book. They're the most common words in English language, I guess. D and and to and they and if and then and would and some and were. So let's look at the next 50. Let's start with 50 and go to 120. Let's see if we now get something more specific about the book. And yes, we start getting some. For example, the most common word that is not this typical English word is Henry. So clearly there's a character in the book called Henry. Then we see an admiral appears 725 times. So clearly there's a character who is admiral. Then there's World Bannersworth. Maybe that's a location. Or Marchdale, I don't know what that is, but these are now book specific things already. Vampire appears 491 times. And there's another strange one, Chillingworth, probably location, appears 397 times, and so on. Okay, so this frequency counting that we have just seen, not only is much simpler, but it's also linear and not quadratic, because we go through the book once, and inside of the loop, all we are doing is testing, is the word in a dictionary, and that's a constant number of operations. Then you add one to some number, else one to some number. So there's constant number of operations inside of the loop. Loop is executed n times, so our solution is linear. So I'm gonna stop at this point.